So, hello everyone, my name is Leonardo Dorache. I'm part of the organizing committee of the Engineering Digital Twins community. Welcome back to a new talk. This will be the last talk for the year 2024, and we'll resume with a new talk on the 30th of January in 2025. We'll come back with new information just before that and some more about the schedule for the 2025. So first of all, today we'll have Anton Basson as a speaker. First of all, thank you very much for willing to give us a talk today. The title of the talk is a design framework for system of digital twins. Anton is a professor at Stellenbosch University. He also holds the Rand Water Chair in Mechanical Engineering and is co-leader of the Mechatronics Automation and Design Research Group of the Department of Mechanical and Mechatronic Engineering at Stellenbosch University. One of his research interests, is developing architectures for a digital twin system for complex systems, ranging from automotive and rail transport to healthcare and water distribution systems. The research group is also active in the area of human system integration, and in this context, holonic software architectures. This talk explores service-oriented reference architecture and design framework for systems of digital twins, emphasizing their adaptability to evolving real-world system and use cases. So thank you again. The floor is yours, Anton.
Thank you very much for the invitation to present some of our work here, and it's really a pleasure. At this late stage of the year, here in South Africa, we have about 30 degrees outside. I think most of you are where it's quite a bit colder, so I hope you are keeping well. I will share. Okay, I cannot share until someone else has stopped sharing.
Yes, I'll just stop.
Okay, so can you just confirm, can you see the presentation screen? Not yet. There we go.
Yes, we can see it.
Great. Get my pointer here. Right. Okay, so as stated, the presentation is on the design work for a system of digital twins. I'll get to what I mean by these terms in a minute or two. Let's see what I can do here. So just to introduce where I come from and who works with me. As stated, I'm in the co-leader of the Mechatronics Automation Design Research Group. I was joined recently, as in the middle of this year, by Dr. Nicole Taylor. She came in after Professor Karl Kruger, who built the research group up with me over many years, moved from Stellenbosch University to Cambridge. And we also have collaborator in our extraordinary Professor Herman Vermaak, who's at a private university in South Africa, and he also collaborates with us. Just a bit about our research group. We work very, very broadly. Some of the sponsors you can see here, BMW, Hortco is a fruit producer organization, Rand Water is a large bulk water utility. Gibela is a licensee of Alstom, I think, to produce commuter passenger trains and maintain them. Mediclinic is originally South African, but now international hospital group. Infinity is a small renewable energy company. And then the Mandela Mining Precinct is a collaboration of mining companies in South Africa. Just to give you a sense of where we're coming from. If you don't know where Stellenbosch is, right down at the southern tip of South Africa and very close to Cape Town. I want to acknowledge that in the presentation today, I will be using work of two of our previous PhD students, or other words, PhD graduates. Carlo Himan developed the design framework that I will be showing you, and the evaluation criteria in terms of the holonic principles is work that arose from Arthur Carter's PhD work that is still continuing, and Karl Kruger played a central role in this work with me. Okay, so a little bit about the presentation. I'll just start with background and objectives. And then I'll give a perspective of what our view of a digital twin is, or at least what this talk's view of a digital twin is, acknowledging that there are many different perspectives about digital twins. Then I will introduce the reference architecture that we use for our design framework, then the design framework itself. And then I will use these holonic design principles to add to some of the considerations one can use to apply when designing these systems, and finalizing with some conclusions. So the objective of this is to present to you a design framework to guide the design of a system of digital twins to represent complex systems. In our focus, we look at digital twins that support data-led decision-making. So in our case, the primary user is often someone who uses the information that is produced by the digital twin to make decisions about the physical system or the real world system that then will affect the real world system. If you start working with complex systems like we do, then designing such a system presents many choices, and the design framework makes it easier. It gives you some of the key complexities, makes you aware of them, and what alternatives to consider and what factors to take into account. The design framework is really a customization of the system engineering process that we've developed in our research group through the experiences we've had. So let's start with the question, what is a digital twin? So in our view, a digital twin is a virtual representation of a real world entity. I specifically do not use physical here because processes and software can also be real world entities in our case. So a virtual representation of a real world entity that facilitates and organizes the integration of data, models, and digital services. So in our thinking, the data ingestion by a digital twin, I think that's widely accepted as a key part of a digital twin. We don't think it's a digital twin unless there's other knowledge added in addition to the data. Let's call that models for now. And then this data and models must be used for something, and in our case, it is digital services. Our work has progressed. Initially, we published the 6-layer architecture for digital twins, which is a single digital twin. Very quickly, we realized if you're working with complex systems, you should not have a monolithic digital twin. So that led to the SLAD, the 6-layer architecture for digital twin with aggregation. So there would be multiple digital twins with a hierarchy involved there. Then we also realized this is too restrictive in some cases. And we developed this architecture, which uses a combination of services, software services, and a digital twin hierarchy. And it is this architecture that it forms the basis of the design framework. I'll give more about this architecture. But we're also currently working in a project on federated digital twins, where the system becomes even larger and wider. So what is our context? We work with real-world entities that are in the operational phase. Often the digital twin is retrofitted, so we do not design digital twins for the design phase. This is for the operational phase, and it could also include the manufacturing phase, because the manufacturing and operational phases often run concurrently in the type of products we work. We look at systems that is complex. It must be complex enough to warrant complex software. Otherwise, it wouldn't make sense to go for modular software. The sort of systems we work with, we expect the physical system or the real world system to evolve over time, and we expect use cases to evolve over time. So for us, this is important, that the digital twin system must be able to evolve as this physical system or the real world system evolves and as the use case evolves. As I said, our digital twin focus is very much on decision support, although we do some work where the digital twin is there to integrate with machine learning and support the machine learning, aggregating, segmenting the data, preparing the data for machine learning type analyses. And we've also done some work, and our architecture does work for that as well, for coordination, where the digital twin will drive activities. As I said, we acknowledge that there are many other types of digital twins, but that's what the focus is for today. So as I said, our work started in manufacturing, and that's where a lot of our underlying thinking comes from. We work in renewable energy. We've done some work in buildings. At the moment, some of our work in hospitals is related to things like smart cities. We've done work In marine, this is the SA Agalas, the South Africa's Antarctic supply ship. We worked in water distribution systems, passenger rail, fruit, mining, healthcare, and automotive. Okay, so getting to the actual reference architecture that our design framework is based on. The key thing is here that we combine digital twins and software services. We think it gives you an appropriate level of interaction and security, so you can segment the system more effectively doing it this way. It gives appropriate viewpoints, so we can have different people with different stakeholders with different perspectives, different areas of interest that we can cater for. It can appropriately filter the information as it's required by the different users, and then it must be able to respond on the load as well. So the architecture has the following main elements. At the bottom here, we have the aggregation hierarchy. And for us, this is the reflection of reality. So we design the aggregation hierarchy around the notion that it must reflect reality. And we try to keep this reflection of reality relatively independent of the use cases so that we do not lock in the system into the use cases. So the purpose here is reflection of reality. These digital twins do include their own services, and these are typically services that only require the data from their digital twin, and they therefore represent fairly stable scenarios that are not expected to change rapidly. As I said, it reflects the reality. We acknowledge the need to aggregate digital twins. In this slide, we still have digital twin instances and digital twin aggregates. In our later work, we've dropped that distinction and say it's a digital twin. Where it gets its data from does not determine the digital twin's nature. And it came up because, for example, if you're working with say a campus digital twin, and the aggregate is could be instance could be a building, and a district could be an aggregate, but sometimes an electricity meter is on a district and not on a building, and then you're going to have to feed data from a sensor directly to the digital twin. So the distinction between aggregates and instances are not very helpful in many cases. The data sources are in many of our cases, the data has already been captured, is already available digitally. So we can capture data directly from sensors or IoT sensors. We go to the cloud, and very often these are external data repositories that are already there. And in our thinking, we have a adapter here between the data source and our digital twin, and that adapter must be thin so that it is cheap to update it. Right, and then the next main component of our architecture is the services network. This is typically a microservices type network, loosely coupled services where there's no hierarchy. They can call each other, they can use each other. So the idea is that these are highly adaptable services, and that you can, as new use cases arise, you may develop new services while the aggregation hierarchy remains stable, because the physical reality typically changes slowly. And then there's some housekeeping to be done in the system, particularly to help this distributed system to work effectively. I'm not going to dwell on the management services. So let's get to the design framework with that reference architecture in mind. As I said, this is from the PhD of Carlo Himon, and I've given the reference here for a paper if you wanted to review where we're coming from. So the idea was to enable a systematic design approach, and we've seen this in our research group. As I say, we do a lot of digital twin development, and we found that this framework really helps structure one's thinking and discussion. So it just tells you in which order to consider some things. It also helps to enable traceability, so that you understand what caused what, or in your design decisions. And it's also an effective way of communicating. We found that if you communicate your design using these steps, the reader also understands it well. So the first phase here at the top of the diagram, I've just zoomed in a little bit, is the requirements analysis phase. So needs and constraints analysis, as one would typically do for a system engineering process, where you determine who are your stakeholders, what do they want. But for a digital twin system, in parallel with that, and they are tightly coupled, so that's why they're in the same phase, you also need to understand the physical system. how the physical system is comprises, what's its inherent breakdown and compositions are, and also what the data characteristics of the physical system is. So the output of this step is a list of functional requirements, prioritize non-functional requirements, a hierarchical real-world decomposition, and the data characterization. So that's understanding the context in which your digital twin system will be working, the real world, but also the user requirements. And then a lot of our thinking then is in the next step in the actual creation of the first level of the architecture, and it really revolves around selecting what digital twins you will use, which you will aggregate and not aggregate, and then allocating software services to digital twins or to this services network and deciding where would be the most appropriate place to put them. So the output of this phase is the digital twin hierarchy, the services that are mapped to these digital twins and the services that are allocated to the services network. So I'm just going to step back. So it's really determining the top level architecture for the hierarchy and the top level architecture for the services network. Stepping back into phase 3, then one starts looking inside those blocks on the architecture and deciding what the internal architecture should be. And the implementation choices start becoming important. So there's architectural design, there's technical implementation decisions to be made, and they interact quite strongly. So that's why they're in the same phase. And then finally, as in any good engineering project, there's evaluation phase where one would evaluate it against the initial objectives to make sure that you meet the functional and non-functional requirements, and there may even be some performance requirements that you want to test from the implementation phase. So it is, although it helps to prioritize the attributes and the steps in which you do it, it's still quite a general framework with many choices. So I won't be dwelling on it here, but as part of our research in Carlo's thesis, you can pick that up. We've also developed so-called design patterns. And the idea with a design pattern is, for example, for performance efficiency, if performance efficiency is a very high priority, then the design pattern gives you some suggestions of the good options to choose and the poor options to avoid, and so on. For we've got these 6 design patterns in Carlo's thesis. In practice, often more than one of these quality attributes are important, and then it still revolves around the designer doing the trade-offs. But the design patterns just helps the designer with a reduced set of, so that there's a reduced set of considerations. Okay, so that's the design framework as Carlo developed it, and that as we've applied it in many of our research topics, and we find it quite useful. But yeah, our research group also does quite a bit of work around halonic systems. It's one of the places where we actually started our work. And we have found that there are, in the halonic world, some design principles that we can also apply to digital twins. And that's from the work of Azar Kader. So I'm not sure how familiar this community is with halonic systems, so please excuse me if I bore you. But I just wanted to give you the key elements. So the notion of a holon comes from way back 1967 from Kushler, and the idea is a holon is a whole in itself, but also one of a greater whole. So there's this autonomy of a holon while it's also cooperating with other holons. And this is particularly useful in complex systems, as I'll be discussing just now. So it links with a complex system notion from Simon that a complex system is stable and almost decomposable when it's formed by simple subsystems. So combining these two notions is really close to our approach for digital twins, in that we subdivide our system into digital twins and services, and actually each of them constitute a holon in its own right. So holonic architectures was originally developed for manufacturing. The people at Leuven van Brussel and his colleagues are well known, the so-called prosa architecture. Many of you will know the Adacor architecture from Leitao, and so on. So there's a number of architectures. Currently, we use Falconars's RT architecture in a lot of our work. So the notion of a holonic architecture is very modular, scalable, independent. The holons are fairly independent. So as I say, our reference architecture reflects some of these properties. Each holon is autonomous. It allows for distributed control, flexibility, and resilience. And they're well suited to dynamic collaborative nature of cyber-physical systems. We use them for that reason. Now, from Simon's work and our own experience, we distilled 4 design principles that we use to decide on, for example, what the digital twin hierarchy should look like and what software services we should use. And the 4 principles are specialization versus generalization, mirroring the world of interest, self-similarity, and complexity of interaction, and I'll go to discuss each of these. So specialization versus generalization. So the notion here is from Simon, is that you should keep your system as generalized as possible for as long as possible. So you want to make decisions as late as possible that restrict your solution space as late as possible so that you can reduce your development time. So in our case, in practice, the way we interpret that is, if I design a digital twin or even a software service, we favor specialization only in configuration data rather than in the source code. So we tend to keep the source code for the digital twin and sometimes the service fairly general, and then just specialize it in terms of the data. And we found that often is very valuable if you're working in a physical system that changes over time. So you can often adapt the digital representation with minimal coding by just changing configuration file. And this reduces configuration cost and risk. Then mirroring the world of interest, we think, is a very important principle. And that is in our digital twin hierarchy in particular. So it must mirror it in the respect that it must be complete, and determining which part of the world of interest you should mirror, that's part of the designer's job. We try to follow the principle that there's a single source of truth. So the digital twin hierarchy in our case is the single source of truth about the physical world. And then to be the single source of truth, it must update and be accurate. So that really matches the digital twin paradigm. So the mirror image of the world of interest needs to keep on updating itself, and that's, as I say, similar to a digital twin notion. So we apply this in the mirroring of the world of interest principles when we decide which digital twins we should have and which services we use. And we found that it's very important in limiting the propagation of changes in the system as the system evolves, because there's very clear boundaries to where a physical change will have an influence, and it also aids in separation of concerns. Then self-similarity. In holons, they should ideally have the so-called fractal nature, where a holon that interacts with another holon should not know whether that other holon actually internally comprises more holons internally. So they are self-similar in that. And that is also, I think, why we've moved away from the distinction between a digital twin instance and a digital twin aggregate, because for the digital twins that work, for external systems that interface with them, they should be oblivious to whether it's an aggregate or an instance. Then you have the so-called horizontal self-similarity, where you can have similarity between holons on the same level, or vertical self-similarity on different levels. So as I said, this is particularly relevant to us in our digital twin hierarchy. And then the complexity of interaction is probably the most difficult principle to apply, because it's against, or it's this notion of how modular should you be. So we look at the frequency of interaction, the volume of exchange information, and the synchronization between interacting holons. And the question often is it multiple holons interacting with complex interactions, or is it one complex holon and got the complex interaction inside? So the choice between those two is quite difficult, and we often go back to the other principles, particularly the specialization versus generalization. If we can generalize it, then we prefer to keep the module separate. If we cannot, then we may want to rather integrate it into one digital twin or one holon. So the conclusion then, I presented to you our design framework and our Holonic design principles that we have found really helps us in designing these systems of digital twins. We very rarely, I can't remember when last we designed a single digital twin. We always think of these things as a system with software, services, and digital twins. It is a customization of the system engineering approach, so we're quite open about that. And we have used this in many use cases, automotive cases, machine learning operations, sustainability decisions, integrating car, vehicle, bill of materials and production information, predictive maintenance pipelines, IoT device management. Those of you that were at the EDT conference, the papers that we presented all built on this framework. We've also worked in rail, as I said, maintenance specifically, looking at lifecycle costing at the moment, and then water distribution systems, and a few others as well. And that's my presentation. So thank you very much for listening, and I'm be glad to answer any questions.
So thank you very much for your talk. This was very interesting. We can stop now the recording, please, and then we can continue with the question and answering session.